All right, so this is just a couple of tips that I'm creating for Lab 5 of Math 215, just because it tends to be one of the hardest labs that we do this semester. And number 1, people usually have a problem with, so I'm going to start with number 2, and this introduces row reduction. Sorry, that should be a minus, and that was a minus as well. And so I'm just going to go over kind of how to do the problem. So yeah, number 2 wants you to make it so the entire first row is zeros. Now if you're doing this in regular linear algebra, you would say our second row, R2, should equal R2, the previous R2, and then minus, this is where we have to decide our coefficient. It would be minus 3 halves R1. And we decide that because we have this negative 3 times 2. So when we times our row 1, in this instance, the first element would be 2 times negative 3 halves. We get negative 3. So we have negative 3 minus a negative 3. So that's where we get that 3 halves from. And this should be just a review of linear algebra up to this point. And so then you get this other matrix where you still have 2, 7, 9, but you'd have a 0 in that instance, and I won't fill the rest of this out yet. And so that's what we'll do to get the 0 in our first row. And so yeah, that's basic linear algebra. To convert that into Python, we have to think how we want to go about doing this. And so we want to eliminate all the zeros. So that would be the second row and the third row. And so the way that I would think about this, if this is our matrix A, then I want to look at all of the rows past my first row. So I'd say, I'd set up a for loop. I'd say for I in range, and I want to not start at 0 because we don't need to change the first row, but rather I'd say for I in range, not 0, my bad. I'd want to start at 1 instead because we want to change everything past the first row. So I'd go 1 and then the length of my matrix because that's how far we want to go. And then I want to say, so let's say it will start at 1, so the second row here. So we want A at I, because it's that row, and I'm just following this format here. We want A at I to equal A at I, and then it was minus, and then we have this coefficient here, which if you recall, was this coefficient divided by that coefficient. So the way that we can write that is say, for this first problem, we can say A I0, because that means the ith row that we're on in the first column, divided by the first entry in the list, because that's all we have to worry about for now. Just like if we did the third row, it would be 1 divided by 2. And then we'll times that, because it's a scalar, by our first row, which will just be A at 0. And so that will be basically everything for problem 2. And so pause it here if you need to write that down. But if we go into problem 3, which, yeah, I'm erasing it now, we need to do it for multiple different rows. And so we'll want to instead have our first for loop set up, and I'm going to use I again, where we want to look at all of the columns that we need to look at. And so problem 1 only looked at the first column, but problem 2 only looked at the first column, but for problem 3 we'll need to look at all of the columns. And so we want to start at 0, and just to look at all of the columns we'll go to the length of A. Assuming this is a square matrix, which it should be. Yep. And so then we'll set up another for loop to do what our old for loop did. And for J in range, and again, we went 1 to the length of A. And again, very, very similar. However, we'll say A at I equals A at I minus, and then this is where we'll deviate a little bit, or these should be J's, my bad. Because say we wanted to change this 2 here. The coefficient that we would look at, or our pivot point, is going to be this 1 here. And so we want to say, we want to first look at this value because we'll have 2 divided by that 1. And so that 2 in this instance would be A, and this is the tricky part. It would be our ith row and our jth column. Because I is going to look at each of these. It's going to switch from this pivot point, this 2, to that pivot point, to that pivot point. And so whichever column we're in, that's the pivot point that we're going to focus on. And so that's why I pick I, and then we pick J, because that's the row that we're trying to get the zeros out of. And then we'll divide that by A, I, comma I, because our pivot point will always be like 0, 0, or 1, 1, or 2, 2, or if we add another row or column, 3, 3. And so that will be our coefficient. And now, rather than timesing it by the first column, we'll times it by whatever pivot column we're on, which will be A at I. And so yeah, this will be your code for problem 3 to make sure you get all of the available 0 spots. And so yeah, pause it if you need to write down that code there. Problem 4 doesn't have too much in it that is super mathematically challenging. Just remember when you're copying down the pseudocode, if you have this format for j equals 0 to n minus 1, the range function never includes the last value that you specify. So you'd want to start at 0 because that's where it says to start. And I'll copy down the rest of this for j in range. And then if you put n, it will go up until n, so it won't include n. And because we want it to include n minus 1, we'll specify n here. And so that's just important to remember. And then again with the m minus 1. And whenever it has this notation, the li comma j, that's going to be the same in Python as li comma j with those brackets. The arrows is the equals, and make sure you're doing the correct matrix multiplication or dot product. Don't say oh, you can't see it there. Whenever you're talking about two matrices A and B, do not times them like that. Do the np.matmul function instead. Okay, so those are just the tips for problem 4. And problem 5 and 6 is what I'll mostly cover next. Because 5, the pseudocode is easy to copy, but I do want to explain what the problem does itself so then you can better solve problem 6, which is backward substitution. So then they have 4, 5, 6, and 9. In essence, what the pseudocode for problem 5 is doing for forward substitution is getting the solution set for this vector. And so if we wrote these out, it would say like x equals 7, 2x plus 3y equals 8. And then 4x plus 5y plus 6z equals 9. And what the pseudocode does is starts at the top, and it says, can we solve just this equation by itself? And it turns out we can. We can say, oh, we have this x value, and it's going to equal 7. You guys can't see that either. Because it's trying to figure out these 3 values. And so it says we can say this is 7 because we don't have anything else to solve for in this equation. And then it goes to the next equation, and it says, oh, 2x plus 3y equals 8. Well, we know what x is because we just solved for it. It's 7. And so if we simplify that, then we get 3y equals a negative 6. So y equals negative 2. And once it solves that, because it has everything except for one variable, we can plot that and say, oh, we know what y is. And then we'll do the same thing on the third row for z, because now we know what x and y are. And so that's how it goes through the forward substitution. That's just what that pseudocode means. And so what that means for your backward substitution is if we had a similar matrix, and instead we could say, so now for backward substitution, you couldn't start at the top row because you have this equation that has 3 unknown variables and we can't solve it. However, you can start at the bottom row because that only has 1 variable z. And so again, writing out these. So yeah, backward substitution will basically do the same exact code as forward substitution, except you'll just want to reverse your for loop. So rather than starting at the very top here, you'll want to start at the end of your array. So you could say like, oh, 6z equals 9, so z equals 3 halves, and so on and so forth. So that's the only change that you'll want to do in your code between forward substitution and back substitution, is just reversing that for loop so it goes up the array rather than down the array. Sorry, up the matrix rather than down the matrix. And then the last note for problem 7 is you're given, you want to combine all these elements together to get your final solution. And so what we're trying to do first is find an x such that a times x equals b. And we know what a and b are. Now, if you remember, our our LU decomposition created a lower and upper matrix that equaled a. And if you recall, our forward substitution created a y such that L times y equals b. And then our back substitution created a x such that u times x equals y. And so you want to return this x that you get. And so what you'll say in your LU decomposition is you want to return, because this is the same x as that x. Those are the same. And so you want to return what we get, and that's just back substitution, I'm abbreviating, what we get from u and y. But we don't know what u and y are. We'll need to specify these up here. Y is what we get from doing forward substitution of L and B. And then I didn't put enough room here. But we get L and U from doing the LU decomposition, or I should say L comma U equals LU decomposition of A. Because we only start knowing A and B up here, and we have to create variables using only our A and B. And so this way, we get an LU based on our A, this way we get our Y based on our L and our B, and then we get our X based on our U and our Y, and that's the value that we'll want to return. So that's for problem 7, and that wraps it up for lab 5. Again, this is just the hardest one. Thought I'd provide some helpful hints, and don't worry, it all gets easier from here. So good luck on lab 5. Be sure to finish it before Friday night. Thanks for watching. Bye.